turning canola oil and potato chips into robot muscles? I'm Tonya Hall, and joining me is Dr. Christoph Keplinger, Assistant Professor of Mechanical Engineering at the University of Colorado in Boulder, and co-founder and Chief Science Officer at Artemis Robotics. Welcome, Dr. Keplinger.
Hi, everyone. Thanks for having me.
Absolutely. Give us a brief summary of your resume and the areas of specialty that you focus on.
So actually, I'm from training a physicist, and then I did a postdoc in chemistry, and then tried to combine those two fields to contribute new things in the field of robotics. And in particular, in a new area of robotics called soft robotics, we were trying to use soft materials that are imitating bio-inspired mechanisms. And in particular, in soft robotics, I work on actuators, so the parts that make a robot move, and we'll be talking in more detail about it later.
So you're working on creating artificial muscles for new generation of lifelike robots, if you will.
Mhm.
What's wrong with the actuators used on most robots today?
Mhm. I think what you can do is, if you imagine a random robot, what usually comes to mind is a clunky piece of metal that's moving awkwardly. And if you compare that what biological mechanisms can do, just like look at the human body, a person in sports and dance, the elegance of movement is just on a whole nother level. And one thing that soft robotics really tries to mimic is this agility and dexterity that biological mechanisms can have. And in contrast to traditional robots, they're made out of usually metal and rigid electric motors. And if you look at nature, what we have is muscles. So like a soft, continuous structure that contracts on external stimuli. In our case, when the neurons fire, then our muscle contracts. And thinking about such a new generation of robots, they would be more adaptable to unpredictable challenges. They would be more safe to closely operate near human people because they're soft-bodied, and potentially they would also be more inexpensive and allow new uses of robots in home environments.
What inspired you to try to solve this problem?
I do think that soft robotics has a lot of implications for the quality of life, a lot of potentials to improve the quality of life. So like I already mentioned, one area where soft robots could really help is that it enables close cooperation with robots, like interactive robotics and co-robots that work closely near people in a company or factory hall. And then the second area is any sort of robot that you would wear on your body. So you can think about some sort of exosuits that would be powered by actuators and enhance your movements. They could even restore some of your bodily functions when you're aging. For example, think about you're 80 years old and your brain is still fine, your body starts to degrade, but suddenly you could wear something like robotic pants or robotic jackets that makes you move again like you're younger. So you could really help such older people maintain autonomy for longer parts of their lives. And then maybe even in the longer term future, you can think about merging with robotic parts, that robotic parts would really replace some parts of our bodies. So first, I think it could be kind of working near people. Second, we could wear some soft robotic parts to enhance or restore human agility and dexterity. And in the long run, we could really think about it as biomimetic devices that are parts of our body. And in some sense, I like to call it maybe robotics for anti-aging, that we really try to improve our bodily functions at old age.
How close are we to really seeing this in full implementation? I mean, do we have the base materials and the software needed, or are those elements still in development?
Soft robotics is a very young field. So my research group and many collaborators around the world are really starting off this large effort. I think it started with something very simple. The first soft robotic devices were largely soft grippers. For example, in robotics, it's surprisingly complicated to pick up something soft like a raspberry or strawberry without damaging it. And there was this idea to use soft actuators that have simple inputs such as pressurized air, and they just deform and they're soft and they're more or less without much external control, without much requirement for computation. They can rather easily pick up things like a raspberry or a strawberry. So this is kind of what started the field a couple of years ago, and it's now a really accelerating effort because people really see this wide potential, how soft robots can improve automation in factory halls like food handling. It can help people that had strokes to kind of regain some bodily functions, and all those things that we discussed earlier. So it's really, I think, a starting effort. And in particular, what I've been focusing on is a key component of every robot is actuators. And there's really almost all traditional robots, they use either an electric motor, traditional rigid electric motor, based on electromagnetic mechanisms. And the first generation of soft robots, what they're using is more or less soft inflatable structures that change their shape based on pressurized air input. There have been some efforts in designing electroactive polymers. This is soft polymeric materials that deform in response to stimuli such as heat or voltage. And when I entered that field, I was really trying to come up with a new generation of actuators that is very closely mimicking the astonishing capabilities of biological muscle. If you think about muscle, it is used in a large range of different animals. It's used in a hummingbird, which can move the wings really fast. It's used in an elephant, so it can be scaled up to deliver really high forces. And it's also in some entirely soft organisms, like an octopus arm, that it's extremely versatile, can wrap around objects, can squeeze through tiny holes. So if we could really design an actuator that is as versatile and adaptable as natural muscle, we could really design almost any type of robot for almost any type of use. And this was really my motivation to have this longer-term effort to come up with something that very closely mimics the performance of muscle. And the astonishing thing about muscle is not really the best at one particular thing, like it's the strongest thing, it's the fastest thing, it's the most energy efficient thing, it can get the largest deformation. What muscle is good at, it is pretty good at all those components. So it's like an all-rounder. It's also tightly integrated with sensing. It can self-heal after damage. So having this comprehensive package of astonishing capabilities, this is really the challenge from an engineering and science standpoint. And a few years ago, I came up with a new idea to kind of combine the versatility of those soft fluidic actuators that I mentioned before based on pressurized air and some ideas from the field of electroactive polymer to create a new technology that we call Hazel artificial muscles. And Hazel stands for hydraulically amplified self-healing electrostatic actuators. And they're based on both electrostatic and hydraulic principles. And what we have shown so far is that they can match or exceed the performance of muscle in all categories that I just mentioned. And that's, I think, the unique quality. They're pretty fast, they're strong, they're energy efficient, and they're based on inexpensive and easily available materials. So there's really hope that we can try to relatively quickly move to the market with such actuators and enable robotic designers to use those actuators for a large variety of tasks. It could be used all the way from biomedical applications, helping people after strokes that I mentioned. It could be used for maybe humanoid robots, give them more lifelike properties, all the way to maybe animatronics to create new robot faces that are really extremely biomimetic in the sense how to deform and able to convey subtle facial movements, like all the different emotions that the human body is capable of showing.
Is it true that one of the muscle materials can actually be found at the grocery store?
It is indeed true. The first generation of the actuators that we built in my lab, so like I mentioned before, they're based on hydraulic principles. So there's a dielectric oil inside those Hazel actuators that's used for hydraulic amplification, and also due to the dielectric properties, it has a very high dielectric strength, which means it can tolerate large voltages before it breaks down. It's actually used in high voltage transformers, and that's what gave me the idea. And then the first generation of muscles we built, they were based on canola oil from the local grocery store. And even the shell material that we're using is based on polypropylene. That's what would be used for housing potato chips. So all the materials it's based on can be made extremely inexpensive. So some of the actuators we make in terms of raw materials, they're on the order of 10 cents. And that's not considering scale up of production.
Where will we see the first applications of soft actuators?
That's an excellent question. So we just founded a company a couple months ago to try to rapidly move this technology to the market. And soft actuators, artificial muscles, they have so many potential uses. And now, like the challenge as a young startup company is to find a good first application to thereupon then like grow the company and attack different fields of use. Let's call it like that. And so our current task is trying to figure out what is a good beachhead market. So where can we go first? What is the first application? And we have interest from many different companies that are interested in potentially using our actuators. And it's our task now to really figure out what is this initial product that like is not too complicated to make. If you think about a prosthetic arm, that's a very, very complex piece of equipment. So as a startup company, right on focusing on such a complex piece of technology, you need a lot of like engineering lead time, a lot of testing, approvals. So that's while that is probably one of the most exciting applications in the long run, that might not be the first use from a commercial standpoint. We're also exploring like using animatronics, like I mentioned, for creating a new generation of robot faces that can more closely mimic what the human body can do. We're also exploring food handling and automation, like I mentioned before, handling fragile types of fruit. That could be another interesting aspect due to the fact that people in those industries, they want to get the human out of the loop due to like germs and again cost saving. And it's at the moment really hard to handle fragile things like raspberries and strawberries.
Dr. Christoph Keplinger, Assistant Professor of Mechanical Engineering at the University of Colorado in Boulder, and co-founder and Chief Science Officer at Artemis Robotics. If somebody wants to connect with you, maybe they want to find out more about how the future of your new business, how can they do that?
One easy way to reach me is over email. So first name, last name at Colorado Edu, Christoph.Keplinger at Colorado Edu. And then I can get you connected with either some of my co-founders from Artemis or some of my research team members from a research group at the university.
Thanks again. And if you guys want to find more of my interviews, you can do that right here on ZDNet or Tech Republic, or go to TonyaHall.net. Thanks for watching.